Today we are going to solve question number 29. Here it is asked to prove that xt, gp is equal to I h cut del g del pt and pt, fx is equal to minus I h cut del f del xi, where g and gp and fx, these function can be expressed as a power series their arguments. So let us do so. So g, first we will prove this relation, then we will prove this relation. So first let us assume that gp can be written as m, n, l, a, l, m, n, p, I, l, p, m, j and p, n, k. Now let us see what is the commutation between xi del g p. It will be summation of m n l a l m n xi comma p I l p j m p k n. Now let us see this. What is this commutation? So xi comma p I l p j m p k n, this can be simplified as xi p I l p j m p k n minus p I l p j m p k n xi. Now let us add some term and subtract that term. So let us first add xi p I l p j m p k n, subtract first term, that will be p I l x I p j m p k m. Then we have to add this term, so we have to add p I l x I p j m p k m minus p I l p j m p k n xi. Now the first term will be, first two term we can write xi comma p I l, its commutation, into p j m p k n, and since xi can be commutation relation between xi and pj, these are two different elements, so this is 0 and xi comma pkm will be also 0. That means we can write it as plus pil, since xi pjm means pj xim, since it commute, that means we can write pjm xi pkm minus pil pjm pkn xi. That means this will be xi comma pi will be I h cut, and there will be pili, so this will be I h cut del pi to the power l, as we have seen in the previous problem. So this will be I h cut del this function and into pjm pkn, and this will be pil pjm, since these two commute, so we can write that pkn xi and pil pjm pkn xi, these two term cancels. Since these two are different from pi, these three are independent elements, so we can write it as pi h cut del pi PIL, PJM, PKN. So let us put in the series, that series, what we'll get? We'll get summation of LMN, ALMN, that will be del I H cut, del PI, PIL, PJM, PKN. That means this will be I H cut. Since summation is over LMN, so we can write it here as LMN, ALMN, PIL, PJM, PKN. So that means this is again I H cut del PI. This term is actually GP, so that means this is G. So we prove the first part of the question 29. Now let us prove the second part, that means Pi comma Fx is equal to minus IH cut del F del Xi. So let us do that. To do so, first assume that Fx can be written as summation of LMN, BLMN, PIL, PJM. Sorry, this is a function of x, so that will be XIL, XJM, XKN. Now we have to Pi comma Fx will be equal to summation of LMN. Since this is a constant number, so a constant number commutes with any operator, that means we can write it as BLMN PI comma XIL XJM XKN. Now let us see what is it. So this means Pi comma XIL XJM XKN, this is equal to, so as we have done it previously, similarly we can here write it Pi XIL Pi XIL XJ XIL, this will be XIL into XJM XKM XKN, and this will be nothing but del minus IH cut del Xi XIL del XIL, so XAM XKN. So this can be written as minus IH cut del Xi XIL XAM XKN. That means this summation can be written as, this commutation can be written as minus IH cut del Xi summation of LMN BLMN XIL XJM XKN. Since this is a constant, not depend on Xi, that means this is actually equal to minus IH cut del Xi f of x. So we have proved the second part also, second part of this relation. Now here we have used one thing, that Pi comma XIL is equal to minus IH cut del Xi to the power L. So let us see whether this relation follows or not. So to do so, first again, as we have seen in our previous lecture, that in some previous problem, that we can write that xi comma a function of p can be, the combination relation can be written as I h cut del pi fp. If we follow the similar steps here also, we can get this relation. So let us do for it once. So what it will be? First let it write pi xil minus xil pi. So we will add some term and subtract some terms. So that means, let us first pi xil xi to the power 1, sorry, xi not xil, so xil minus 1 minus, let us minus some term. What will minus? Will minus xi pi xil minus 1. So we have to add this term pi xi pi xil minus 1. Let's subtract some term, that let's subtract xi pi x, will subtract this term, will subtract xi pi xi to the power l minus 2. So I have to add this term again. So xi square pi xi l minus 2. Similarly, if we go like this, we'll get last one term, that will be xi to the power l pi, and xi l minus l will be 0 minus xi l pi. So this term cancel. So if we closely look in the first two term, we will get pi comma xi to the power l minus 1. Similarly, in the second term, we will get xi. From this term, we can write it like that, pi xi into xi to the power l minus 2 minus this term. So let it write in this fashion, pi xi to the power l minus 2 minus this term xi pi xi to the power l minus 2. Similarly, we can express like this, and the last term will be xi l minus 1 pi xi minus xi pi, there will be xi and pi. So that means how many terms we will get here, that will be when in this term there will be 0, x to the power 0, that corresponding to 1, this corresponding to. So whether what is the power here, if power 1, then what are the terms, second term, then it is the nth term here, it is nth term. That means what we'll get from here, minus I h cut, since we know this commutation relation, xi to the power l minus 1 plus here from here also xi I h cut minus I h cut, so that means minus I h cut xi to the power l minus 1. Similarly, we get this n similar term, that will be minus all the term, actually the similar sign, so that means all the term is minus last term will be minus I h cut xi to the power l minus 1. So this will be lth term, so that means minus l I h cut xi l minus 1, that means that is minus I h cut del xi to the power l. So we have used this relation here for proof this relation. So we have proved the a part of the question 29. Now let us check what is the b part of the question 29. Here it is asked, evaluate x square comma p square and compare your result with classical Poisson bracket x square comma p square. So first evaluate part p quantum, that means we have to express x square plus p square. So what it means? It means x x and x square p square minus p square x square. This means x p minus p p x. So let us add some term and simultaneously subtract these terms. Minus we have let us add x p x p. We have to add this term x p x p. Now subtract px xp. We have to add this term again. That means to add px xp. Now let us subtract one term, that will be px and I have to add again this term px and last term is p x. So if that means that will be x comma p, these two terms xp minus px xpp plus from here these two terms, that means xp minus px xp. Here from these two terms px xp minus px xp minus px. Now here plus px, this will be px. No, this will not know px. There will be, this term will be p xp minus px x. That means this will be IH cut. So this will be, every term will be IH cut. This is also IH cut. This is also IH cut. This is also IH cut. So IH cut xp plus xp plus px plus px. That means 2 IH cut xp plus px. So it is the quantum result, quantum mechanical result. Now let us check what is the classical commutation relation. X square commutation, it is not commutation, it's actually Poisson bracket. So classically we know that this means x square del x del p square del p minus del p square del x into del x square del p. This is 0 since x and p is independent. That means here we'll get 2x and 2p. That means 4xp. Since in classical mechanics xp is equal to px, that's why this term add and this will be 4. So let us write it in this fashion: 2xp plus px. That means we get the, again from here also we can see that we get the classical version of a quantum mechanical version of the classical Poisson bracket will be, if we add IH cut into the classical result classical result. Obviously, we have to consider one things in our mind, that is the commutation between xp is equal to px. It is true in classically, but it is not true quantum mechanically. So we have to always remember this thing in our mind. So now we have solved the question number 29, both A part and B part. Now we will solve the question number 30. In question number 30, it is asked the translation operator for a finite displacement is given by tau L is equal to exponential e to the power exponential minus I p dot L by h car, where p is the moment vector. Evaluate the xi, pi. That means we have to evaluate this. And from the previous question, that is question number 29, we know that xi, any function f p can be written as I h cut del f p del pi. So let us use the similar result here. So from in question in question 30 in part A, that means xi comma tau L will be I h cut del pi tau L. What we'll get? I h cut will get exponential minus I p dot L by h cut into del pi minus I p dot L by h cut. That means I h cut times minus I by h cut times e to the power minus I p dot L by h cut times, if we express dot product as pi li, p dot L can be written as p dot pi li plus pj lj plus pk lk. That means from here only the first term survive, since pj and pk independent of pi. That means we'll get here from multiply li. That means li times these will cancel, minus I plus I will be 1. That means it will be minus I p dot L cap by h cut. So we have evaluated the first part of the question 30. Now let us see the question of B part of the question 30. So here it is asked, demonstrate how the expectation value x change under the translation. So suppose up and when B part, in general x will be some alpha x alpha. Now these alpha, the position coordinate of the state change by this translation operator. Now that means, now what is the expectation value in this transformed state? That will be alpha dash x alpha prime, and the dual correspondence of this state will be alpha tau dagger. And this tau, let us see one thing, that means alpha tau dagger x, this will be tau alpha. Now alpha tau dagger, these can be written as x tau minus tau x. We have to add another thing here, plus we have to add this term plus tau x alpha. That means alpha tau dagger x comma tau alpha plus alpha tau dagger tau x alpha. and tau equal to tau into tau dagger equal to tau means e to the power minus I p dot l by h cut. Tau dagger will be to the power I p dot l by h cut times e to the power, sorry, the tau dagger tau tau is e to the power minus I p dot l by h cut. This is e to the power, this is the e to the power, this plus this will be 0. E to the power 0 means 1. So, and this result can be also written as, since this is actually tau l, so you can also write li tau l. So use here that alpha, this will be li, this will be li tau, and there will be tau dagger alpha, this will be 1. This 1 means unity operator, that means it will be x expectation value in the previous state, in the previous state alpha, and this will be li tau dagger means again 1, and that means alpha plus x. And if the state previously normalized, then it will be x plus li. So from here we can see that the expectation value in the new transform state is equal to expectation value of the old state, expectation value of the position of the old state plus li. So that means after the transformation, the position of the state, the expectation value of the position of the state will change by amount li. So it is asked in the question B. So we have solved the question 31. Here it is asked, in the main text we discuss the effect of tau dx prime on the position and the momentum eigencase, and on a more general state case alpha. We can also study the behavior of expectation values x and p under the infinitesimal transformation. And alpha goes to tau dx prime alpha only prove that expectation of x is equal to expectation of x plus dx prime, and expectation of p goes to expectation of p. So let us check that. And we know that tau dx prime is 1 minus I p dot dx by h cut. And we also know that tau dagger dx prime tau dx is equal to 1. Now let us check the expectation value of x in the transformed state. That means alpha prime x alpha prime x alpha prime, and we know that alpha prime is equal to tau alpha. That means it can be written as alpha tau dagger x tau alpha. It can be written as alpha tau dagger x tau minus tau x plus tau dagger tau x alpha, and this is equal to unitary. This is, since this operator is unitary, that means tau dagger tau equal to tau dagger is identity operator I. That means here it will be alpha, and we know that x comma tau dx is equal to dx. In our lecture, from our lecture, we know that means it is equal to tau dagger dx alpha plus alpha x alpha these, and let us check what is the value of tau dagger dx into dx. It will be 1 minus I 1 plus, if tau dx equal to 1 minus I p dx, then tau dagger will be 1 plus I p dot dx by h cut times dx. And since dx is very small, and if we only uh, take the first order term, then it will be dx. That means this term can be simplified as alpha dx alpha plus, this will be the expectation value of x in the old state x. That will be x plus dx, and since alpha is, we assume that alpha is normalized, that means our x, our expectation value in the new transformed state will be x, its expectation dx. This is the similar result as we have seen in the question number 30. Now let us check the second part of the question, that transform value of the momentum. So to do so, let us uh, calculate the commutation relation between tau p and tau dx. Pi tau dx. What it will be? It will be minus I h cut del xi tau dx. Since tau dx is only function of p and dx is a constant, it doesn't function of xi, that means this will be 0. So from that means pi tau dx is equal to tau dx pi. So that means the expectation value of p on the transform state is equal to alpha prime p alpha prime, and it will be alpha tau dagger dx p tau dx alpha. Since this commutes, that means alpha tau dagger dx tau dx p alpha. This, since this is unitary, that means this is identity operator, that means alpha p alpha, that means x it is in the old state, that means p in expectation value of p in transform state is actually equal to expectation value of p in old state, p in old state. So that means we have solved the question 31.